Okay, welcome everyone to our Institute for Quantum Studies seminar this week. I'm very happy to introduce Frank Narducci visiting us from the Naval Postgraduate School. I just wanted to give a few words of introduction for Frank. He graduated from Drexel University and then went on to the University of Rochester, where many of us also have a connection to. And he did his PhD under the famous late Lynn Mandel, studying his thesis about photon correlations in single and multi-atom systems. So after graduating from Rochester, Frank spent the rest of his career with the Navy in various different roles. And he's an expert in atoms. He'll tell us today about atom interferometry. He moved then to the Naval Postgraduate School in Monterey, California, where he's currently the department chair. In addition to his scientific activities, I know Frank very well as his role as an editor in Physical Review A. Many of you probably recognize his name from emails from Physical Review A as well.
Those are the emails that everybody ignores because it usually there's a review coming.
Anyway, so Frank, we're very happy to welcome you to Chapman and to hear about your work on atom interferometry.
Thank you, Andrew. It's a great pleasure to be here. I've been looking forward to this visit for quite a while. I don't know about being an expert, but at least I can talk somewhat knowledgeably about atom interferometers. So the title of the talk today that I sent was Dueling Atom Interferometers, a T-cubed atom interferometer, and a very tall atom interferometer. But as I started to construct the talk, I don't know why this is not working. It was working 10 seconds ago. Give me 1 second. I know what the problem is. There we go. I realized that there was way too much to be crammed into one talk, so I changed it a little bit. So I'm just going to talk about the T-cubed atom interferometer, a very tall atom interferometer, and then I'm going to give you a commercial just to highlight some of the other stuff that I'm doing. Just for the interest, there's postdoc and faculty positions available in my department. If you're interested and in a position to take advantage, let me know. So the outline of my talk today, I will tell you about this T-cubed interferometer. This is work that I have done in collaboration with the group of Wolfgang Schleich in Ulm. Matthias Zimmermann was his PhD student, now working at the DLR, which is the German equivalent of the Space Agency, and Maxim Efremov, and Jeff Lee is my postdoc, was my postdoc. Then I'm going to tell you about Tall Atomic Tower that I'm working on with a bunch of my students, and again, Jeff Lee, my postdoc, and then the advertisement is some work that came out of the work with Wolfgang Schleich as well. And just in case I forgot to tell you, we're looking for postdocs and faculty positions. I had to delete some of the discussion that I wanted to make on dual atom beam interferometer gyroscopes accelerometers. I work for the Navy, so the Navy likes to see relevant things, and accelerometers and gyroscopes sounds like a Navy relevant thing. So I won't be talking about that today, but certainly you can ping me if you want. So I'd like to start by doing a quick atomic physics 101. I apologize if this bores some of you. You may be very well familiar with it, but at least it puts everybody in the same starting plane, and we'll go up from there. You probably may not be familiar with T-squared scaling in atom interferometer, so I will tell you what that means. And then our take on how to change that and make it a T-cubed. What does that mean? And how are we going to do it? So we'll talk about possible realizations. I will tell you a little bit about Raman spectroscopy and Rabi cycling in magnetic fields, and then with magnetic fields that have a gradient. We have to have a gradient to the effect that I'm after. And then I will tell you about the T-cube data that we got that we were really excited about, maybe. I'll tell you what that maybe is all about. There's a mystery there, and then conclude that section. First half is kind of theory, second half is kind of experiment. Then we'll move on to the next part of the talk, where I will tell you about my crazy idea. I like to advertise it as my Ig Nobel Prize submission. And when I'm done, I think you will all agree that this is a perfect Ig Nobel Prize submission. I'll tell you about some of our proposed experiments. We're going to change atoms. Why are we doing that? I'll talk about that. Some very simple calculations, if I have time, and some pictures of the apparatus. So theory and experiment go that way. Okay, so let's launch in and let's talk about a T-cubed atom interferometer. So let me start with the very, very basics. And again, if you are already familiar with light atom interaction, particularly with a two-level atom, you could take a nap for about 6 or 7 minutes. But I just remind you of a few salient points. If I have a simple two-level system and I want to interact with a single mode laser field, what happens? Well, a couple of things. If you scan the laser, you have a transition. The transition typically has a natural line width that's handed to you by nature. Yes, you can go narrower, but you need to do some heroics to do that. But power broadening is actually very easy. So you can typically make it wider, but you really have to work to make it narrower. And I point to just one thing. I have to remember I can't actually point with a laser pointer on the screen. But typically for the atoms that we're using, which are alkali, the natural line width is typically about 6 to 10 megahertz or so. Okay, so if you start looking at dynamics instead of something steady state, which is kind of what you're doing when you're doing scanning the laser, you need to put in spontaneous emission by hand. There's no nice analytic solution that I'm aware of, but this is kind of what it typically looks like. You turn the laser on and you ask the atom, what state are you in? And the atom kind of cycles back and forth, but because of spontaneous emission, there's a dephasing and the oscillations damp out for strongly driven systems. For weakly driven systems, you get a behavior like that. So this is very reminiscent of what I was doing as a graduate student under the direction of Len Mandel. He had the same amount of hair, but it was a lot less black when I was a student there. But this is kind of some of the measurements that we did, where we were looking at Rabi oscillations within a two-level system. And again, because of spontaneous emission, you get the dephasing. Okay, now now we've gotten our PhD, we know what we're doing. We're going to try three-level atoms because two is too simple now, right? So what happens? So we consider a three-level system. This is the three-level lambda system. And what are we going to do? So we turn on one laser. In this case, I'm going to take the laser, I'm going to make it far-off resonance. So if it's far-off resonance, it does nothing, pretty much. Okay, so what? Then I can do the same thing with another laser and another transition. Again, so what? But when you put the two together, now something happens. You start cycling the population back and forth between your two ground states. And you kind of never go through the excited state. So here's some data from my lab. Looks remarkably like the data I just showed you, except that the timescales are completely different. So here we are on the nanosecond scale. That's because the line width is I said it's a few tens of megahertz. That's consistent with timescales of hundreds of nanoseconds. I will show you some data where we've got very narrow lines that are typically of order 10 kilohertz or so. And so this is on a much longer timescale. There is still dephasing here. It is not caused by spontaneous emission.
Frank, what are the units of the x-axis on the top plot?
Microseconds.
Microseconds.
Yeah, sorry, I got cut off. So we do see some dephasing, and that's caused by two things, which I can talk about later. Okay, so the point though is that the two-level atom physics that I described in kind of the introductory slides happens in this system here, and our two levels are these levels 1 and 2. Okay, and that's being driven now by the composite of my two laser fields. Okay, and so let me give you some basic terminology. You've probably heard this, but just in case, when we take the atom and we're cycling back and forth through the states, so this is a plot of turning the laser on at time t equal to 0, and just letting it evolve. At some point, the probability of finding the atom in the excited state is complete. It should go all the way to 1, and that's what we call a pi pulse. That's because your argument here, when this is equal to pi, corresponds to that. The 2 points that I want to highlight, though, is that we talk about pi pulse and we talk about pi pulse times, but I want to remind you that it's when the product of the Rabi frequency times time is equal to pi. If I change the laser intensity or I change the detuning, my pi time changes. Okay, more interesting to me is the pi/2 pulse, where now the atom is half excited, half not excited. And the interesting thing about that is, okay, we have a coherent superposition of ground state and excited state. But if we think about this from the perspective of, let's say, momentum recoil, this says that, well, this part of the atom wave function after the pulse remained in the ground state. So nothing happened, so it remains in its original momentum state. But the part that got excited must have absorbed a momentum kick. So you're in this weird state where the atom is in the ground state or the excited state, but in two different momenta. And that's what forms the basis of a beam splitter. So when we talk about atom interferometers, we start with the atoms in the ground state. Apologies, I switched notation from 1 and 2 to G and E all the time. I don't know why, I just do it. So we start with our atoms in the ground state. I will apply a pi/2 pulse. That's what we call the beam splitter. As I've already alluded to, the atom partly recoils, but partly doesn't. So the atom starts to go in two different directions. We let the atom sit in the dark and just accumulate information for us. So we wait some time t. We apply then a pi pulse, whatever was in the ground state gets promoted to the excited state, vice versa, with corresponding momentum kicks. So the atoms start coming back towards each other. And then we wait another period of time t, and then we close the interferometer with a beam splitter. So those of you who know optics, which is probably in this room, this should look remarkably like a Mach-Zehnder interferometer, and that's exactly what it is, except we're using atoms instead of light. So things to highlight. If I calculate the phase, what is the phase of the interference pattern that I see on the output of the interferometer? Well, if I configure this to be a gravimeter, for example, it scales like t squared. The way you can think about it, it scales as t squared, which is essentially an enclosed area argument. The length of this arm is t, the length of this arm is t, and so roughly speaking, t squared is the enclosed area. So that comes as no surprise, because when we think about the analogy to things like ring laser gyroscopes, the sensitivity of the interferometer scales with the enclosed area of an optical loop. So same thing with atoms. So the point, though, is that this interferometer phase scales like t squared. Okay, so that's probably a recap for almost everybody in the room, maybe. If not, and if I blew through something very quick, please stop me. I meant to mention I don't have to go through these. I do want to show you my crazy idea. I want to make sure I leave time for that. But apart from that, please stop me if you have any questions.
So maybe just as a pause here. So usually if you used to have two different frequencies, then the phase you accumulate is then linear in time. So that would be like the time dynamics. And you're saying on top of that, you also have this position dynamics as well. There's also essentially a phase that goes like linear in time.
Correct.
So when you combine the two in this loop, you get the t squared. This is your argument.
Correct. Yes, with the additional caveat that when I do this in principle on resonance, so that linear term goes away. Because the linear term is detuning times time.
Right.
So that goes away.
Okay.
So this is in principle pure t squared. Okay, so let's take a closer look, and I promise we're not going to do tons of algebra. That's too boring. So this is my version of doing the algebra. We calculate the phase. The calculations are not especially tricky. They're just a little tedious, but there's nothing past almost literally freshman physics involved. You just need to know how to calculate the phase, and that's it. But what happens? You have terms that scale like t cubed, and they float around your calculations, but then in the end, they drop out, they cancel. And so you're left with a pure t squared scaling. And so you would say, hey, wouldn't it be nice if we could keep those t cubed terms? Why? Because that means the sensitivity of my interferometer will scale faster. Instead of, if I extend my time by a factor of 2, and the sensitivity would scale and give me a factor of 4 with t squared, I can get a factor of 8 in sensitivity. So that would be great if we could do that. Why do the terms cancel? And the answer is basically due to the symmetry of the problem. We assume that as the atoms go around the two paths, that gravity, for example, is the same. Well, what if gravity is not the same? Okay, so here is an example of an interferometer where the symmetry is broken. So in this particular example, I now have designed my interferometer to have state selective gravity or no gravity. So if I could wave my magic wand, okay, I have not told you how we're going to do this at all, right? But if I could wave my magic wand and say, okay, if the atom is in the excited state, it'll feel gravity. But if it's in the ground state, it will not. And then I go through and do the calculations. This would scale like t cubed. And this was the problem that was presented to me when I went to go visit Wolfgang Schleich a number of years ago. And we came up with this idea. Okay, but how do we do this? How do we turn gravity off? In fact, it's worse, right? We're not turning gravity off. We have to make it state selective. Yes, sir.
Is that the only way to break the symmetry?
No, you could break the symmetry by adding gravity gradients to the device as well. That gives you a similar t cube scaling, but you could look at it from a different perspective. So when we do it our way, you can think about the phase as coming from the gravitational potential. No, sorry, comes from the kinetic term. The gravity gradients come from the potential term. So no, not the only way. Okay, so how do we turn gravity off? And like I said, worse, we have to make it state selective. Okay, well, we don't. We can't turn gravity off, right? That would be great, but can't do it. We could go into space, right? There's nothing that stops us from doing that. We could do an experiment on the ISS. They're running experiments all the time, but we need it to be state selective. That's the key. It's not just turning gravity off. But what we have shown is that if I pick a magnetically sensitive transition, then you have to account for magnetic fields because they're magnetically sensitive. And so when you do that, you find that states that are not magnetically sensitive experience acceleration, which is just the local gravity. But states that are magnetically sensitive will experience local gravity plus a term that depends on the magnetic field gradient. The magnetic field gradient gives you essentially an extra acceleration term. And that breaks the symmetry now. And this is now a state selective way of doing things. So you can envision essentially that we do an experiment where we apply a pi/2 pulse, we put the atom in a superposition of an m equal to 0 and an m equal to 1 state, magnetically sensitive, insensitive, magnetically sensitive, acceleration g plus magnetic field gradient. Also, in the particular configuration that we are using, we are actually going to go ahead and use co-propagating fields instead of counter-propagating fields. I haven't really talked about the direction and what that does for us, but in that particular case, it'll cancel our t² term, at least the first order. So we have a pure t³ interferometer. It's not just a t³ and a t², and what's the coefficient in front of t³? Is it bigger or smaller than t²? All of that goes away. Pure t³ scaling if you do the interferometer the way we've talked about it. Okay, but this is the challenging problem, right? So all of you probably know that there was a debate when we were when the country was first setting up our power grids, and the discussion about DC versus AC power lines, and the DC camp lost. So magnetic noise is everywhere. So we have to deal with that. In principle, that's a technical issue. And we think we've solved our issues with that. But we also have a more fundamental problem. And the more fundamental problem is our friend Jim Maxwell lived, and he wrote down his formula that says if you have a magnetic field gradient in what we call the z direction, for us, that's the vertical direction, you're going to get one in the x and y direction, and you can't get around that. That's going to be a problem for us. That was actually the subject of a series of 3 papers written by some permutation of Schwinger, Scully, and Englert, where these papers are actually called the Humpty Dumpty papers. where they were basically arguing that if you try to do atom interferometry in magnetic field gradients, you can never pull your atoms apart and bring them back together again and expect it to work because of the magnetic field noise. And so you can pull the atoms apart, but you can never put it back together again, just like Humpty Dumpty. So that sounds like bad news for us, right? Because isn't that exactly what we're trying to do? And the answer is yes, that's exactly what we're trying to do. But there is good news on the horizon. This paper came out from the Ron Folman group, where they were trying to do experiments in atom interferometers with magnetic field gradients, and it worked. I will explain to you what this means in a little bit. But what this meant for us is, hey, they got it to work, so if they can do it, we can do it. So that's kind of the idea. Okay, so what does our experiment look like? So this is a cell that was built for us by a company called Cold Quanta. Anybody working in cold atoms knows that group. I've known that group very well. So they're located outside of Boulder, a spin-off of CU. Our experiments start with a two-dimensional cold atom 2D trap on the backside. The atoms stream out over here and they get caught at the bottom where we do a 3D trap. So the atoms just hang out there. And in all the experiments that I'm going to describe, the atoms get launched up our tower. We apply our pulses of light to do the interferometry, 1, 2, 3, however many we do, but the atoms continue to go up. And at the top, we do detection. We turn our laser beams back on and ask how many atoms arrive in the excited state, and kind of assume that those that are not in the excited state are in the ground state. Our early experiments, we just flashed a laser beam on and measured. In later experiments, we actually do a time-resolved version. We have a thin sheet of light right in front of the detector, and as the atoms fly by, you get a pulse. That becomes relevant to what we're doing later. So this is one of my favorite pictures that we took. This is what the experiment looks like. Essentially, of course, if we were running an experiment, the atoms are in the dark. As they get tossed up the tube, you wouldn't be able to see them. This is, of course, just a movie so you can see what the atoms are doing. But this is kind of what it looks like.
So there's fluorescing as they go up the tube?
It's fluorescing just for the movie.
Yeah.
But not for the interferometer.
Got it.
That's correct. Yeah. And this is basically a stitching together of a bunch of still shots. So we launch, take a picture, launch, take a picture.
Got that.
Okay. Okay, so what do I need to worry about to make this experiment work? Well, this effect is based on having a magnetic field gradient. I didn't go into the math, but I'm telling you that that's what we need. And so I need to have a linear potential. I can't just put a coil around my apparatus and expect it to work. It has to be linear. It can't just be linear plus a couple of quadratic term and a cubic or whatever. As the atoms go up the tube, if they're in a magnetic field gradient, then the resonance is changing. So I will have to chirp the laser as they go up. Flat wavefront, I'm not going to talk so much about. So we have a gradient, magnetic field gradient across the atom cloud. That's going to be interesting for us in just a few minutes. And the atom interferometer has to close. I'll talk a little bit about that in a few minutes. Okay, so here's one of the plots that I promised. This is the transition that most people use when they're doing atom interferometry. This is the so-called clock transition. It's called the clock transition because you use it for clocks. If you're trying to measure time, you don't want to measure magnetic fields, right? So this is the magnetically insensitive transition. It's quite narrow. One of the things I forgot to highlight on the 3-level atom slide is that the line width is under our control, not given to us by nature. If I leave my laser pulse on for longer, in principle, this gets narrower. Okay, but in rubidium, you don't have a single transition. You have a whole pile of magnetic sublevels that you have to deal with. So your entire spectrum looks like this. There's 11 transitions. You can see that the peaks over here are wider than the peaks over here. And this is precisely because of the magnetic field gradients.
Is there a reason you use rubidium and not cesium?
just because those are the lasers we had, but this works just fine in cesium as well. Okay. Okay, so what we do is we first of all start by mapping out what the magnetic field looks like using these Raman transitions. So I will remind you that the separation between these peaks depends on the magnetic field strength. And so if I want, I could just look at my spectrum, either the whole thing, or in the interest of time, we typically only look at the middle three. Okay, and take a scan, and then let me back up. What we do is we prepare the atoms. We toss them up at a particular point in the height of the trajectory. I apply a laser pulse, which is intended to drive one of these transitions. The atoms go all the way to the top, and I measure, and then we start the process again, changing the laser frequency. So I scan this at one height. Once we're done that, we do it again. Once we've done that, we do it again. This is typically an overnight run for us. One of the things I love about lasers that we have in particular is that we lock them and they stay on resonance forever. They don't move. In my days of Rochester, I was thrilled if I could get my laser to stay put for 45 minutes. So this is a big advancement. So we can use this technique to measure what the magnetic field looks like as we go up our tower. So this is a representation of taking these type of spectra as we go up the tower. And so here you see the clock transition. It doesn't move as you would expect. Here, this is what the magnetic field looks like. We haven't done anything to linearize it yet. This is what it looks like if we do nothing else, if we just run the experiment.
Probably I missed it, but how do you get around the problem of having X and Y magnetic field in X and Y direction?
I have not addressed that yet.
Okay. And what's the, what is the scaling for these colors? How strong is the gradient?
The gradient is 150 microtesla per meter. That number it's just a design number. There's nothing fundamental about it. It's kind of one of those, we'd like it to be strong, but not too strong type of argument. Okay, I guess I can skip in the interest of time. One of the things that we had to worry about is, okay, I showed you pictures of what Rabi oscillations look like. Okay, and on the clock transition, that's fairly easy to do because there's no magnetic noise. But with magnetic transitions, it does become challenging. And so what we've done here is, again, we do that same type of experiment where we toss, but instead of changing the frequency, well, we do change the frequency. But going up here, this is not arrival time anymore. This is now pulse duration. So this maps out, if I take a slice this way, you get oscillations. And the point of this graph is to show that in our system, we have shielded it well enough and control the magnetic field noise well enough that we can now see oscillations on a magnetic transition, not on the clock transition. And I know that for a fact because this is not at zero detuning. Zero detuning for us is the magnetic insensitive transition, the clock transition. So this is non-zero, it's one of the magnetic transitions. This was a significant challenge because those of you who might be working in cold atoms know that to make cold atoms, you need to have a magnetic field on, magnetic field gradient actually, on, that we have to turn off. And as soon as you turn it off, now you've got eddy currents and all sorts of other nasty things circulating in your system. So you got to wait for that all to die away. So we've done that, we put shielding up, and now we can see oscillation. So the idea now, at this stage of the game, is that our magnetic sensitive transitions are coherent enough to see oscillations. So great. One detail, which I'll just very briefly talk about. If I consider the location of the atoms in the tower, I've got a cloud of atoms, think of it kind of an extended ball, but there's a magnetic field which is a magnetic field across that ball. So the atoms on one side of this ball of atoms hit resonance as we scan our laser frequency at a different location, which translates to a different time when we do the tossing of the atoms. So one of the things that we did, which helps improve our data, is we have a de-skewing algorithm where we basically just kind of take this ellipse and reconstitute it back to a circle. We get much better data. Okay, so that's a detail. If you're interested, there's a reference there. Okay, so I've already talked about calibrating the field. Let me skip that. What we do to make this effect work is we have two sets of coils. So these red coils here are the coils used for trapping the atoms. They don't have anything to do with the experiment after you've got the cold atoms set. But then we have what we call a solenoid around the atoms in the tube. And it didn't come out very well, but you also have these red coils, which are gradient coils. So we have the ability to tailor the magnetic field kind of however we want. We did a whole pile of calibrations and then looked at the magnetic field. So once we did that, we found that the magnetic field is quite linear. So it is quite linear over the extent of our, not the whole tower, but at least a significant fraction of it.
Sorry, what is the red versus the blue coils meaning?
Sure, I did not explain that very well. Blue coils are just solenoids, so just kind of magnetic field strength.
Yeah.
And then the red ones are wound in an anti-Helmholtz configuration, so they give you a gradient. So it's 2 knots.
Okay.
It's slightly more challenging than you think about it. Just turning on a magnetic field and a field gradient. We do have a shield around this system, which is not completely closed because they can't close it from underneath. So we do have some field leakage through. So we have to kind of calibrate that out. But looks pretty linear. And so we're like, okay, good. Now we're in good shape. We have to chirp the laser. I talked about that. I'm not going to get too much into the details because I really want to get to my crazy idea. But as we toss the atoms up the tower, we do the same experiment with the Rabi oscillations, except we have to keep the atom in resonance. And so we're able to do that as the atoms go up. And here's some of the data that proves that. Okay, let me just kind of get to the meat of it. So we've done a little bit of interferometry. The slides that I skipped did some of the interferometry. It shows that we have coherence out to maybe somewhere between 500 and 1,000 microseconds, give or take. This is just fringe visibility as a function of time. You see that the clock transition remains coherent all the time. For our case, we've got a couple of different magnetic transitions that dephase certainly much faster, so there is still magnetic noise, but out to a millisecond, we should be able to do the experiment. Question, good enough? Let's find out. Let's just do the experiment. Well, one more thing. The atom interferometer has to close. What do I mean by closing? I mean the atoms start to pull apart and they come back together again. The point of the Humpty Dumpty papers is that you can't do that. Well, if you have a magnetic field gradient in the vertical direction, you can think about the atoms going up. They're now in separate states, separate accelerations, so they start to pull apart in a vertical direction. You now apply a pulse, they start to catch up, but because of the field gradient, they don't close. If they don't close, they don't overlap. If they don't overlap, no interference, experiment is over. Turns out that if you apply a pulse sequence that looks like this, the interferometer will close. I still haven't addressed your question yet. Okay, but in the vertical direction, it closes. So let's try it. And we say, look at this. This is great. Right now we're thrilled. What are we looking at? We are looking at the interference of the atoms as we change our time between pulses. We are expecting a t-cubed dependence. We ran the experiment on the clock transition. That's the yellow data. Even if you squint hard, you probably can't see any oscillations, which is good because you shouldn't. Okay, but if you look at the blue, right, the blue is the same pulse sequence now done with a magnetically sensitive transition, which should show us t-cubed. If we do a fit to this interference pattern, here's the scaling that we're looking for. You'll notice that we get a fit parameter of 3. Yes, this is great. And, you know, is it reproducible? Sure. So that's all good. So why am I acting like I'm not quite so happy? I'm not quite so happy because we look a little bit more carefully at the data. And in particular, where does this minimum occur? This minimum occurs at about a millisecond. That's just the parameters of our experiment. Okay, but if I go and I do the theoretical curve that connects this minimum with the experimental minimum, this phase factor depends on 3 things. The laser wavelength, which is very well known, gravity, which is very well known, and the magnetic field gradient, which I claim is very well known. But we have a factor of 2.5 difference here, 1 millisecond here, 2.5 milliseconds there. Because of the t-cube scaling, this means we would have to be wrong about our magnetic field gradient by a factor of 8. 2.5 cubed, it's almost 10. So what's going on? Don't know. That's the mystery that I'm going to leave you with. Let me highlight very quickly here. Atom interferometer needs to close. I'll skip that part. The problem that we have to work out. So it seems to work. That's great. We did a bunch of tests and a bunch of reworking of our magnetic fields. We actually have a more linear magnetic field now than we did before. And the interference has vanished. Our field gradient is better and we have no interference. What's going on? We think that part of it is this problem here. So to answer your question, the field gradient in the z direction that pulls the atoms apart, I can control with pulse sequences. I can put the atoms back together again. But in the x and y direction, I can't. There's no kind of force or change in acceleration that puts it back together again. So the atoms just fly apart and don't come back. So they don't close in the x and y direction, they close in the z direction. Okay, so let's turn the argument around. Why did it ever work in the first place? And we believe the answer to that is that maybe in our first experiments, we got the atoms to work right on the center line. And right on the center line, because of the way, if you work out the magnetic field, you don't have that gradient. It's multiplied by 0, essentially. So stay tuned on future experiments for that. So in the 5 or so minutes I have left, 5-ish, 5 or 10.
We're going to go till, in principle, to 11.
Okay, good.
So
Okay.
we got time.
All right, good. I will take my time. I was leaving time for questions, but I will go a little slower. Okay, but now we're going to change gears entirely. So I am working now on a 30-meter tall atomic tower. So let me give you a perspective. The picture that you saw of the atoms going up the tube, the scale of that is about 10 centimeters. So we're the Navy, we don't do things small, everything's big. So we're going to go and build a 30-meter tall atomic tower right on the campus of NPS. So this is the famous Del Monte Hotel, where all the elite Hollywood types used to go to get away from it all, right? My building is this tall, is this long one. It's 5 stories of offices and labs. Go to the roof, you go up the elevator to the 6th floor. And once you get to the roof, and by the way, this is the view roughly, then there's actually a superstructure that goes up 1 more floor. And so that's where we're going to be building our interferometer. It's going to be right about there.
Before you go on, Frank, maybe just to say, going back to the earlier topic.
Sure.
So in terms of the motivation, usually the reason you build these very sensitive atom interferometers is you're trying, for example, to measure acceleration of gravity to many decimal places. That's one of the big motivations.
Right.
And so if you get t-cube scaling, that gives you better precision on the local magnetic field gradient or local magnetic field at that position.
It depends on how you do it. So the phase depends on, forget the laser wavelengths, it depends on the product of G and field gradient.
Yeah, yeah.
So if you know G very well, you get a field gradient, and if you know the field gradient, you get G. So you could do both.
Right. And so in terms of your motivation for developing this, does the Navy envision shipping these around the world to make very, sensitive measurements of gravitational field for, looking at what's underneath the surface or things like that? Can you talk a little bit about
Sure.
why the Navy's
Motivation,
interested?
sure. So basically everything you said. One of the things that the Navy and DoD in general might be interested in is tunnel detection. And so how do you think about tunnels from a physics perspective? It's the absence of local gravity. Tiny little bit out to the 9th decimal point. But if you could measure with that kind of precision, then in principle, you can think about an atom interferometer that's flying along, it's measuring local gravity. Here's the tunnel, all of a sudden the local gravity changes a little bit, and then you pass the tunnel and it comes back again. So that's kind of the motivation for a gravimeter. And that's actually going to be the motivation for this one as well. On the other hand, I could use that device to measure gravity and determine gravity very well. And then if I know gravity very well, I can measure magnetic field gradients with this device as well. I might be interested in field gradients if I'm looking for submarines. Submarines, again, from a physics perspective, is just a chunk of metal. That's it. And a chunk of metal has a magnetic moment. And so magnetic anomaly detection is based on exactly that. Other motivations for atom interferometers in general could be accelerometers and gyros, which I didn't talk about. Okay, so let me tell you about this experiment. So this is a project that I'm doing in collaboration with some of these folks. So this is my postdoc that I mentioned. This is a former student, a lieutenant commander, and these are 2 current students, an ensign and a commander. Master's students and PhD students. Oh, in case I haven't mentioned this already. Okay, what are we thinking about doing? So everybody chuckled when I said this was an Ig Nobel Prize submission, so you already know what the Ig Nobel Prize is, right? It's a satirical one. The way I think about it is it's for a project that makes you go, well, that's really stupid, right? And dumb, and why would you ever do that, right? Why would you want to study how spaghetti strands, right, fold or something like that, right? But then when somebody tells you what the motivation is and what the science that oh, that's kind of interesting. So that's exactly what this project is. So everybody's welcome to come visit me in the physics department. And we have a Foucault pendulum, just like many other physics departments across the country. What does a pendulum do? Well, the Foucault pendulum does 2 things. Number one, of course, it swings back and forth, but it also, the axis in which it swings rotates. And so in Monterey, that's about a 36-hour or so period. Okay, so now the question becomes, well, I'd like to measure the period of this pendulum. And that's where you say, well, that's retarded. Just do what you're doing right now. You just look at it, you count the number of swings, and you've got a clock here, and so you count 100 swings or whatever you want, and then divide by the number, and then you're done. What if I tell you, though, that you're not allowed to look at it? Okay, so for example, this pendulum is on the ground floor of my building. The atom interferometer that we're building is in the basement. So you have no line of sight to the pendulum. How do you tell if the pendulum is swinging? In fact, I do that often with my guests. I bring them by, I show them the pendulum, and then I go downstairs and I say, is the pendulum swinging? And they say, yeah, we just looked at it. And I say, well, how do you know? Maybe I turned it off when you weren't looking. Right, so how do you know? Well, you look for a disturbance in the force, right? How do we detect the swing? You can measure the disturbance in the force. It's changing local gravity because it's a mass that's coming closer and further away from your interferometer. And so that's how we'd like to measure the period of our pendulum. Okay, so you say, well, okay, still sounds like a dumb experiment, right? Or very complicated and very challenging way to measure something that you should be able to otherwise measure trivially. Just go and look at it. Why might the Navy be interested? I'll tell you that in a second. So this experiment is affectionately called the pendulum. Those of you who know about Edgar Allan Poe will recognize that title. I gave a brief to a Vice Admiral just the other day, and he had no idea what I was talking about. He was surprised. So the way we do our experiment, here's our pendulum.
You mean our military aren't literate?
I didn't say that. Sure, we'll go with that. You've been reading one too many tech manuals or something. So this is the ground floor of our building. This pendulum works precisely. Oh, let me back up. When my building was built back in 1956 or so, for reasons that we have no idea why, they put 4 elevator shafts in the building, but they only put 2 elevator cabs in the building. So we have 2 unused elevator shafts. So one unused elevator shaft houses the pendulum. Here, this is all blank. There's nothing here. Well, you can't do that. You have to put something there. Let's put an atom interferometer. Why not? So this is kind of the geometry of the experiment. Pendulum is swinging back and forth here. Right below it is just a space where we put our computers and other stuff here. Our optics table is all the way down in the sub basement, where basically the cab of the elevator would have gone if it came down to the basement floor. We have our atom interferometer. The atoms are caught somewhere down here. They get launched up the tube. This picture isn't exactly accurate. Our first baby version of this experiment, the atoms will come up to about this height, and we can do experiments. Once that's all worked out, we're just going to keep going all the way up to the roof of the building. Okay, so then we, in principle, measure the swing of the pendulum, right? What's the real purpose? Why is this? Okay, that's not as dumb as it sounds. Those of the people who have done this type of experiments in the past, where they have demonstrated the sensitivity of atom interferometers, have done so by doing the following. They have an atom interferometer, or perhaps 2, running together, and they bring a half ton of lead in close to one of the interferometers, and then average for a long period of time. And then you move it away, and you average for a long period of time, and so on and so on. So it can take 24 hours to measure the presence of this lead back and forth. If we're talking about doing something like tunnel detection, you're asking about motivation. I don't have time to take a UAV, for example, put an atom interferometer on it, and hover over a tunnel for 24 hours, and then move 2 feet and hover for 24 hours, and so on and so on. The typical battery for a UAV is about 45 minutes, if you're lucky, an hour. So we have to do this on much faster timescales, operationally relevant timescales. An operationally relevant timescale could be of order a second. Well, our pendulum is swinging at about 10 seconds. So if we can detect the presence of the pendulum swing and map out that oscillation, then we are doing these measurements on operationally relevant timescales. That's the idea. Also, we're going to have a very big apparatus. We can get away from a lot of the issues that you run into when you try to shrink things down. And so we can basically push the precision of the instrument to its fundamental limit before we start doing the shrinking problem. And my favorite one is this experiment is literally going to depend on things like the phase of the moon, right? Because the phase of the moon just gives you an additional gravitational term, right, that you have to worry about. How better, and then you have all sorts of other issues. How better to teach not only our future DoD leaders, but just physics students in general, physics, when you give them an experiment and say, you need to know a lot of physics to make this work, and your degree depends on you making this work. Great motivation to learning a lot of physics. So that's the idea. Also, let me highlight this real quick. And that is, we do plan to make it a user facility. So eventually when it's built, it'll be computer controlled, of course, but you can log in from the outside. So Andrew can sit at his desk and say, I wonder what would happen if I do the following pulse sequences in a 30-meter tower, and I'll give him access and he'll do it on his computer and he'll get the results. And then send it to me as a peer editor. So that's the idea. Okay, I'm not going to talk about this. I've already kind of talked about this. This is the level structure that I talked about in rubidium. The issue that we're going to run into is 30 meters is a very long way to take atoms and toss them. And in particular, we have to make them really cold because they're going up and they're still expanding. In the case of my earlier experiments, we're only going 10 centimeters. The movie you saw is about 50 milliseconds, and the atoms don't expand very much. 30 meters, the atoms have √6 seconds to go up, or 2 times √6 seconds to go up and come back. We need to make the atoms really, really cold. How do I do that? In rubidium, I'm not going to even bother. We're going to change atoms. I just want to highlight what changing atoms does for us because I think it's cool. I can do laser cooling of the blue transition. The blue transition is very strong. It grabs atoms for me, grabs a lot of atoms for me, but doesn't leave them particularly cold. It'll leave them about the same temperature as rubidium, actually a little hotter. So it's going in the wrong direction. But I can also switch, and use the 689 transition, which is a red transition. It's a much weaker transition, much narrower. So it's not very good at gathering atoms, but if you've already gathered them, it's very effective at cooling the atoms off. So literally, if I change from a blue cooling laser to a red cooling laser, do nothing else, I will drop the temperature of the atoms by a factor of 2,000. And so that's at least a very good start on the way to tossing my atoms. Let me just hit a few other highlights. So the question is it possible, right? Can we do this? Well, let me do the problem simple before I do the problem hard. I'm going to assume that the pendulum is above the atoms. Is that true? No, but at least it's a good start. And I can just model gravity as a time-dependent gravity, do the calculations. The amplitude is associated with the amplitude of the swing with this distance. So that's about a nano-g or so. And we have verified that the atom interferometer closes. And we need to get the kind of gravity resolution that we want. We need an interferometer time t of about a second, total interferometer time of 2 seconds. And so that translates to about a 5-meter tall tower. So our baby version should do it. So this is not exactly the most recent picture. We have our scaffolding already up. You can't see the roof, but you're just about to see the roof. There is a hole in the roof for the tower to go through. Down here, we already have some of our vacuum systems in place, but we don't have the tower system in place. But we do have all our lasers down there. Here is our blue laser. And there are a couple of lasers under that plastic wrap as well. Oh, so that's what it will look like. Okay, so at this point, let me just stop here and tell you, this is kind of the stuff I talked about. A T-cubed atom interferometer, a tall atomic tower. I didn't talk about the equivalence of Hamiltonians. The commercial that I'm just going to give you, by the way, postdoctoral faculty position, in case I haven't mentioned it 4 times already. We basically look, the commercial is, we have a paper that is coming out, if we can just finish the last 1% of it. Somehow the last 1% takes 90% of the time, where we have looked at the phase of the atom interferometer under different conditions and how do we interpret the phase. And the answer is, it depends. Let's see all this and go, wasn't planning on covering it. Basically, the phase of the interferometer has a dynamic phase and a geometric phase. But if you look at it from different frames, from different perspectives, these 2 contributions change. They do not remain the same. The phase, of course, has to remain the same because that's what you measure. That doesn't change. But the interpretation of what's causing the phase changes. Okay, so that's just a commercial. I didn't explain that at all. So if you walk away from this going, I didn't understand that. Right, I did not explain it, but there's a paper that will explain it. That's what it is there. So let me stop here and just take any questions. And thanks for your attention.
Thanks, Frank. Questions? how do you get the atoms to go up? Do you blow puffs of air on them? What do you do to make those atoms
It's a
go up?
great question. It's one of my favorite steps of the experiment. So what we do is we first of all turn off the magnetic field, leaving the lasers on, so they're kind of in a molasses, so they don't go very far. Then once we want to do the toss, I have a laser beam from underneath and a laser beam from above. I detune the laser beam from above a little bit further away and detune the one from below a little closer to resonance. So now there's a net force in the vertical direction.
This is the same way you're doing the cooling of the atoms as well as the detuning of the laser.
Yes, the way I would phrase it is, it's the cooling lasers that I'm doing this detuning with.
Yeah.
But what I like about this is that, okay, now there's a net force because one's further detuned, one's closer to resonance. But as the atoms start to move, there's a Doppler shift and the lasers start to come back onto resonance. So you are cooling in the moving frame. And by calculating that detuning, once you know what that detuning is, once you've established it, you can determine what velocity are those atoms with zero detuning. You can, and that gives you your launch velocity.
So are you pushing on it the whole time or just in the beginning?
Just to get it to go.
All right, and so the bigger kick if you're going to the 30 meter, you got to do a big detuning to really kick those atoms hard.
It's going to be so that is going to be one of the research projects is how can we toss that far without significantly heating the atoms?
Right.
And so I think that we just have to look at it. Yeah, it's going to have to be a very big kick.
Yeah, and this whole column is all in vacuum, right?
Correct. Yep. The typical vacuums we work at are about 10 to the minus 10.
Yeah.
So all the way up.
I have a very naive question.
Oh, I hope I can answer it.
Suppose I mean, your room is 4 meter, right? I think this is 4 meter maximum. Like you can
yes.
have, like you said, 5 stories. That means 20 meter. Where's the rest of the 10 meter?
So 5 stories is actually this is a great question. So 5 stories kind of gets us can't point very well, but to the upper floor, the upper enclosed floor. Now, if you want to walk around the roof of our building, that's one more floor, so that's the 6th floor. And then on the 6th floor, there's a superstructure where the elevator cab would have gone through. So that's the 7th floor.
Okay.
And we're up about a little over waist high. And so once you account for that, plus the fact that the basement, remember, we're below the basement. It'll take me forever to get there. But we're below the basement. Here we go. Stop. This is the basement floor, so we actually have a whole other, so that accounts for the additional 10. And I should say there's nothing special about 30 meters. If our building had been 1 story shorter, okay, then it would be, 26 meters or something. It's just that this is all, elevator, there's elevator shaft, there's nothing there. So once we get past this point, I have to go all the way up. There's no stopping point.
Frank, would it be of any interest to measure, we're referring to the pendulum now, not the amplitude of the pendulum, but its frequency?
Well, we get the frequency by looking at, so we're going to try the experiment 2 ways. The first way we're going to do it is synchronize with the pendulum. So we'll toss the atoms and take a measurement every time the pendulum is over here.
Yeah.
And then change that offset and kind of do that. So we should be able to see that.
You're sort of like taking snapshots of the.
Yep. But as pointed out by my sponsor, that's cheating. Because that means I need to know what the pendulum frequency is to be able to do that.
Right.
So once we show that we have that sensitivity, then we're going to have to come up with a way of making that same measurement, but not doing it that way.
Yeah. So from the point of view of the atoms, basically the pendulum is fixed in one position.
Yes. Yeah. And then to avoid the synchronization problem, we'll probably run the atom interferometer a lot like a lock-in amplifier. So we'll run the experiment at non-commensurate frequencies, and we're just going to get nonsense, right? 0, like a lock-in amplifier.
Right.
But then once you are at the right frequency, you'll question.
Yeah, I was wondering, so you model the pendulum as like something like G plus G pendulum sine omega t. So what's the relative scaling of the G there? Oh, okay, 10 to the power minus.
This one, yeah, so that's 9.8, this is, 10 to the minus 9. So really small against something really big. So that is a challenge.
Okay, I think we're out of time, so let's thank Frank again for the time. To join us for lunch. Just meet in my office at around